Good evening to everyone, good morning to whoever is watching this video. And today we are going to continue with our series on our artificial intelligence project. And today we are going to be looking more into cleaning of our data set that the link to our data set has been put out, and we're going to clean our data. So basically, it's going to be an end-to-end machine learning pipeline. You're going to build a model in the end, but we are going to also be doing more of the cleaning of the data. So an introduction, basically it's going to be an in-depth analysis of our data set through various data set cleaning techniques and visualizing our data. Visualizing our data is basically through different plots, graphs, bar graphs, histographs, in whichever way we are going to look into detail, visualize our data, and furthermore, we also plan on splitting our data set into three sets: the training set, the test set, and validation sets. This you can check out on our code base. The link will be below the video of, of our notebook, and it will be evident of how we separated our data. So here we have our heat map. Now remember, through our past tutorials, our data set has 5 fields that are numerical. So, and hence they help us plot a heat map. Now, the importance of the heat map basically helps us show the correlation of, of each attribute to another attribute. And here our attribute in question is the price, if you can see here, because we are mainly interested in the price. And of course, the darker the color represents a higher correlation with that attribute. So you can see that if you look at price and price, it's white because those are the same values. So in any case, it will just be white. So from our view here, we can be able to judge that the ID and the airbags have like the strongest correlation with price. And basically, a heat map helps us assess these correlations of our different data, of our different attributes. So our different attributes, our independent variables that we use to define our dependent variable, which is the price in this case. Not forgetting that our model is about car price prediction. You're predicting the prices of used cars. So obviously, that's why we have because the ID uniquely identifies each entry into our data set. Then we have the price that we are interested in. We have the production year, the cylinders, and the airbags. Okay. First, we're going to look at an outlier plot. Plotting our price, we discovered that our price has an outlier entry into our price, which is here, and we can visualize that through plotting a scatter graph. And that scatter graph can help us identify this outlier that is within our data set. Now, this can easily be seen through plotting of a graph. That's why we need to always visualize our data set. To go on, we managed to drop the outlier and plotted the scatter graph again, and we can discover that on dealing with outlier, in this case we decided to drop that field, as you will see through our code. I realize that our data set, though it has some of the outliers, but we can now visualize it and see that basically we have some other 3 outliers that are within our data set. So we again plotted a box plot. Now, of course, box plots can also help us visualize our outliers. And of course, box plots help us determine the median, the interquartile ranges to see where most of our data is lying. And here you can see these were the 3 outliers that we had visualized from outlier plot with the scatter graph. And here we are plotting the price. So since our data set has multiple numerical fields, I decided to plot individual box plots for the numerical field. Now we have an attribute called levy. Now levy is the tax that was incurred on the vehicle on the time of purchase. So our levy also we plot it because it's also an independent variable that has a significance correlation with that dependent variable, which is the price. And it too has an outlier that we can see here. And those are the outliers we have to sort out, because outliers can cause bias or inconsistencies within our predictions. So we also have mileage. Now, mileage is the kilometers that have been driven by the car. Like usually, this is like the how they determine the aging of a car. So usually cars that have a higher mileage tend to be cheaper in real life. That means the car is older because mileage is the kilometers the car has been driven. And it too is a numerical field because this is kilometers. We clean. If you look to our code base, we dealt with that data because our data set had the mileage actually in its data type as object, because it had a numeric and the value kilometers attached to it. So we have to clean our data. In this case, you have to drop the kilometer and then convert the remaining fields into a numeric that we could be able to plot, which is evident here, because we cannot plot a string or an object attribute type. So we have to clean the data and convert. This is more evident in our code base that has been uploaded in Cargo, and we'll put out the code base link in the description. So now the patterns of interest here, we decided to sketch out. In this case, we're sketching the price and the levy. I'm sorry, I didn't capture but this is the price, and this was the levy. So we discovered that, of course, we plotted very many these this kind of graphs for each of the fields, and we discovered that no attribute on itself, like let me say, no independent variable has any correlation with our price. No single attribute has any pattern with our dependent variable which are determined, which is the price. But in actual sense, to discover that a combination of all these different independent variables, the levy, the mileage, are the ones that constitute a certain pattern for the price. So our takeaway here was, after plotting this graph, we discovered that no independent attribute, let me say levy alone and price, that the levy and price have no pattern. There's no pattern in this guy between levy and price or mileage and price. But if you combine all these different independent variables, the levy, the mileage, the production year, all these things, when you combine them, that's when they come up with a pattern that helps us determine the price of the vehicle. So here I decided to visualize on the levy, our levy attribute in a histogram. Here we can see our outliers here going out. We also managed to visualize our mileage, the kilometers driven, and we could see our outliers. The three outliers are notable here, and the frequency is over here. The frequency, because whatever is on the y-axis is basically the frequency, and these are the future independent plots of our data. Now we created a validation data set. Now here's a snapshot from our code base on Cargo, and in this case we took a snapshot of our code base, explaining 20% of our data is allocated to validation, which in turn is used for the hyperparameter tuning. So we used this is a snapshot here. It's how we split our data to get a validation data set. And you can see here we took 20% of our data of our data set to be used. Now, how did you do the hyper tuning? Now, we built a model using linear regression and the use of R2 score to assess its performance. Now, basically here we build the model. We built a model using linear regression because we employed the linear regression technique, and we're assessing how the input, we're assessing the linear Now we're assessing the performance of our linear regression techniques using the R2 score. So in this, it helps us to tune our hyperparameters. In this case, we would run the model, then would assess the R2 score. Then would drop particular attributes, I could say columns, and then would run and then we would run and determine the R2 score. So the more when we dropped certain fields, like let me say those, we'll realize that our R2 score was going, meaning our model was more accurate. In this case, we were able to determine the hyperparameters. And the hyperparameters in this case were the airbags, the fuel type, as you see in our code base, the mileage. The levy was also dropped because on running the R2 score, realized that when you drop the levy, the accuracy increased. So in that case, that was we dropped the levy because it was no longer a hyperparameter in this case. Because if you remember, our dataset actually has 18 attributes or 18 columns, but in the end, our hyperparameters turned out to be five, five columns of five hyperparameters, and that were set using our R2 score. Whenever we would run the code, would determine the accuracy, drop more columns, and hence we're able to do our hyperparameter tuning. Thank you very much. That's the end of today's presentation. Have a nice day. Thank you very much.